very happy to be here and to be able to give this talk about effective residual finiteness and the question of Higman. So let me start by discussing computability of finite quotients of group. When you have a residually finite group, you may want to use this algebraic assumption to solve the word problem. But what's usually difficult in solving the word problem is proving that something is not the identity. And if you know that finding a non-trivial image in a finite quotient is sufficient, you may want to leverage this. And similarly, when you have finite rigidity for some groups, you may want to use their finite quotients to distinguish between these groups algorithmically. So this might give you a method to solve the isomorphism problem. Now, when you are studying finitely presented groups, there is always an algorithm which lists all the finite quotients of your group. Because to know if a given finite group is a quotient of your group G, you just have to check whether those finitely many relations hold for some generating family of the finite group. And I'm not talking about time complexity, I'm just saying it's, in theory, feasible. What happens for infinitely presented groups? So, definition, a group has computable marked finite quotients if there is an algorithm for the following problem. On input, you give a finite group and a map from the generators of G to the generators of the finite group. And as output, you should decide, well, does this map define a homomorphism? And let me give you an example, a quick example. Here we have a presentation for the Lamplighter group on top. So it's an infinite presentation. And on the bottom, you have a finite group. And you want to know, is this finite group a marked quotient? And here a marked quotient means I want to say to send A to A1 and T to T1. Well, this T1, it has a finite order. And once I know it has a finite order, well, there is a morphism like that if and only if it factors through the group obtained by adding the T to the N as a new relation. But once you do that, those infinitely many relations go away, and you're left with a finite presentation in the middle, and you can check whether or not you have a quotient. This is a very simple example, but we have examples of the same phenomenon, which are non-trivial. So a result with Bartholdi and Pernack, groups with presentations in EDT0L have computable marked hyperbolic quotients and computable marked abelian binary-potent quotients. So this extends results of Bartholdi, Eck, and Hartung. And the phenomenon is exactly the same. You have those two groups, and you're saying, is the bottom group a quotient of the above one? And I have infinitely many relations, and for some reasons, here it's equational noetheriality, I'll be able to reduce those infinitely many relations to finitely many relations. All right, the second definition. So if a group is effectively residually finite, if there is an algorithm which, given the words on the generators that define the non-identity element, outputs a finite group and a morphism such that the image of the element is not the identity in the quotient. Of course, because we have residual finiteness is defined by a for all exist statement, and we can make it effective in this way. And this passes to subgroup. A finitely generated subgroup of an effectively residually finite group is also itself effectively residually finite. Now, a theorem of mine. There are three residually finite groups. The first one has unsolvable word problem, but still it has computable finite quotients. And it is effectively residually finite. So we know exactly what the quotients, the finite quotients of this group are, but it doesn't imply that the group has solvable word problem. The second one has solvable word problem, but it doesn't have computable finite quotients. Still, it is effectively residually finite, so we can enumerate sufficiently many finite groups to separate all points, but we can't enumerate all the finite quotients. And the last one has solvable word problem, but it's not effectively residually finite. The first group can be constructed using a result of Slobodskoy on the universal theory of finite groups, undecidability of the universal theory of finite groups. And let me also note that this last group, G3, answers the problem of Harlampovich, Myasnikov, and Sapir, because it's a residually finite group with solvable word problem, which cannot be embedded in a finitely presented residually finite group, because these having computable finite quotients, they are always effectively residually finite. And so we have the following conjecture, the Higman embedding conjecture for residually finite group. A finitely generated group embeds in a finitely presented residually finite group if and only if it has decidable world problem and it is effectively residually finite. But this is very open. Why am I talking about this today? Well, you heard Tuesday in Matteo's talk that there is ongoing research about computable profinite groups. And I'm not stating the definition again. André Nice has the following theorem. A finitely generated group is a subgroup of a computable profinite group generated by computable paths if and only if its world problem is co-semi-decidable, meaning you can list the words that define non-identity elements, and it is effectively residually finite. And an easy fact also to notice is that when you have these computable finite quotients, you can list all the finite quotients, then the profinite completion of your finitely generated group will be a computable profinite group. And so, because of this theorem and this fact, the properties that I gave you of G1, G2, and G3, you can express them purely in terms of embedding in computable profinite groups or having a computable profinite completion and things like that. And it gives so these results are relevant somehow with respect to this new line of research that André is conducting. All right, and a question of Higman now. You take the group of permutations of the natural numbers, and you take its subgroup consisting of computable permutations. And Higman asks, what are the finitely generated subgroup of this group of computable permutations? And an easy remark is that any such group is a pi group. It has co-semi-decidable world problem, because when you have a computable permutation, you can notice that it's not the identity because it moves something. And Morozov in 2000 shows that this is not a sufficient condition. And André, again, remarks that an effectively residually finite pi group does embed in this group of computable permutations. Because if you can list sufficiently many finite quotients to separate all points, you have an action on the natural number, which is faithful and computable. And he asks, well, find a residually finite pi group which does not embed in this group of computable permutations of the natural number. And with Armand Arbignan, on Tuesday, we said that we can construct such a group. But what's unfortunate is that our obstruction is the same one as the one given by Morozov, because in a group of computable permutations, you have an algorithm which, given an element of prime order, outputs its order. And we can build a residually finite group with solvable world problem where this is not possible. You have elements of prime order, you know its order is prime, but you can't compute what prime it is. And I'd like to find other obstructions. I have some in mind. For instance, a finitely generated subgroup of this group of computable permutations must have a decidable subset. Not too hard to see. And problem, is there a finitely generated group with co-semi-decidable world problem that doesn't have a decidable subset? And the same question for finitely presented group is open. So finitely presented group with no decidable subset. And this is interesting because this would be a strengthening of the theorem of Miller from 1981, saying there is a finitely presented group with unsolvable world problems such that any non-trivial quotient also has unsolvable world problems. So this is saying no normal subgroup defines a decidable property in our group, and the question is it possible to say no subset defines a decidable property? All right, I'll stop here. Thank you for your attention.